So, just a quick disclaimer here at the beginning of the video. If you don't want to watch it, you can skip on the timestamp down below. So, the thing is, I've been trying to make this fire detecting project work on my current Arch plus Hyperland environment, and it's just been a nightmare because on my current project, I use something called MSS to take multiple screenshots of my screen and create a stream of frames that I can then feed into my object detection algorithm that will detect if there is fire on the current stream. The thing is, MSS is not supported on Hyperland because Hyperland uses something called Wayland compositor instead of using something called X11, and therefore I cannot use my current script directly. I would have to find another screenshotting utility that would enable me to take multiple screenshots of my screen to create a stream of frames and then use these frames to feed my object detecting algorithm. But the problem is Python doesn't have many libraries that support Wayland, and thus the only library I've been able to find that supports Wayland is PyScreenshot, and it supports Wayland via three different ways: XDG desktop portal via dbus, or GNOME using also GNOME dbus, or in my case, because I haven't been able to make any of these two first options work on my environment, using Grim as my screenshotting utility. And if you take a look here at the Grim GitHub, it's just basically a screenshotting utility, and it takes screenshots at very slowly. And the problem is, as I'm trying to create a stream of frames, the speed of the screenshots is really something that interests me. If it's too slow, I won't be able to achieve that 60 plus FPS on my stream, thus enabling me to live stream my screen and actually make it my code or my algorithm detection feels like it's in real time. So, but the Grim is not the main objective of Grim was not to create a fast screenshot utility, it was just to create a screenshot utility. And if you're using that for this purpose, it's fine, because for a user that just wants to take a screenshot, if it takes up to 300-400 milliseconds for a screenshot, it doesn't make any difference, it's just a screenshot. But if you want to stream, as I stated before, you need faster ways to stream your screen. Thus, the only option I have, being Grim, just simply does not work. And just so the TLDR of this message I want to get across is, if you're gonna do a project similar to what I'm doing here, please do not use Wayland that only supports Grim. In this case, do not use Hyperland. You could try GNOME using dbus, because you could try other streams or other backends or screenshotting utilities to screenshot your screen. And these are all the options that this library enables you to use. And if you're using GNOME, you could use GNOME dbus, GNOME screenshot, or free desktop bus if you're on XDG desktop portal. Okay, so TLDR, do not use Hyperland for this kind of projects, because it won't have any screenshotting utility that is fast enough for you to actually stream your screen in Python. Okay, so I'm talking about Python. There might be other languages or other utilities that work, and it might even exist in Python, but I haven't been able to find it yet or test it. So that's what I'm telling you. Currently, it looks like this. If I try to if I try to stream my current environment, it looks like this. So on the left side is my current cursor, on the right side is the stream of frames, and the FPS is just terrible. Therefore, it's just unusable for my current project. So it just doesn't work. So that's it. Just code it on other environments that would support MSS, because MSS is a good utility for this kind of projects. Let's go to the video. Yo, what is up guys? So today I'm gonna bring you an update video on my fire detecting project, and we'll start by going over a brief showcase of the project, and after that I'll go over an explanation of the tools we have used and a little bit of how they work and how you can replicate it if you want to do something similar. So let's move on. So moving on to the showcase here. So this is the piece of code that I've shown on my previous video, and what it essentially enables me to do is to create a stream of frames given a specific source, either my screen or my webcam, and we can feed that stream of frames into our fire detecting module, and enables me to visualize on a window that is streaming those frames, and we can see if the model is detecting fire correctly. So in order for us to use the model to predict fire on a given frame, we're using the Ultralytics library, and it also enables us to choose a device, either our GPU or CPU, but luckily we have our GPU because it's a lot faster than rendering things on our CPU. And we can also feed the path to the model that we want to use. So this is the model we have trained to detect fire. And let's showcase now with our screen capturing function here. So if we take a look at this function, what it essentially does is it creates a slice of my screen of the size 640 by 640 right in the center of my screen. And this is very important because the accuracy of the model on images that are 640 by 640 is a lot higher than on images that are on different sizes, because the model has been trained on images that are 640 by 640. And to actually create this stream of frames, we need to take multiple screenshots of that region, and for that we're using the MSS library utility tool. And this enables me to reach around 30 screenshots per second, or 30 FPS. And for each frame, we're feeding this function called detect fire and smoke. We're currently only detecting fire, but I was planning on detecting smoke as well. But for now, this the smoke detection function here, it's useless. So we get each of those frames, we feed into the model prediction function, and it gives us some results. And if we have found a fire in that frame, we also have access to the bounding box region where the fire has been found, and we are using the OpenCV library to actually display the bounding box around the region on that frame, so we can actually visualize if the model has predicted fire correctly or not. And that's essentially what it does. So in order for us to visualize that, we're using the OpenCV image show function that enables us to create a little window where it streams back the frames we are printing, so we can have a visual feedback. So let's start this, and you can see here the window will pop up, and this little window here is just representing a 640 by 640 square in the center of my screen. We can then go to websites that have fire images. So as you can see here, as I scroll through the web page here, the model is taking, this piece of code is taking multiple screenshots of this region on my screen and feeding each of those frames into my model. My model is predicting fire somewhere, and then we're able to draw these bounding boxes where the model has predicted fire on that specific frame using the OpenCV module. So that's it. But as you can see, the accuracy of fire detecting is not very high because, as I will explain a little better in the later part of the video, the model has been trained on a free dataset. So if you need more accuracy, you can train on a bigger dataset that you're probably gonna have to pay for. But for now, this is very good for a mockup, and it is good enough. You can also do it on videos. So for example, let's start playing the video. As you can see here, the FPS is not the same as my screen, but it's high enough. Let me lower the volume here. And we can also look for things on thumbnails and images around the other websites and other web pages here. But that's it. For a mockup, it works pretty well. So now let's showcase the second stream. In this case, let's try to showcase using our webcam. So now, moving on to the webcam showcase, we just have to swap the source we want to get the frames from. In this case, we want to get the frames from our webcam, and for that, we're going to call this function capture webcam, and it's pretty similar to the capture screen function. The only difference is that instead of capturing the frames from our screen, we're capturing the frames from our webcam, and for that, I'm using the OpenCV video capture function that enables us to receive this capture this capture object. Then we can read the frames from it and transform it into the 640 by 640 we want to get a higher accuracy for fire detection, and we feed each of these frames back into the detect fire and smoke function that we've already talked about. So we then feed the frame into the model, we get the results, check if the frame has any fire in it, and if it does, we draw the bounding box around it using the OpenCV draw rectangle function. And again, we're just getting the visual feedback with OpenCV image show. So let's run this real quick. Let me open it again. So we're just gonna have this webcam here. There you go, that's me. So the FPS is not that high, it's not 60 FPS as I've talked about, but it's good enough. And first of all, I'm gonna showcase with a lighter, and I'm gonna use myself as the background. So if I use myself as a background to make the life of the recognition or the machine learning model easier, because it's easier to understand there is a fire right here. If there is a darker background, I can move the fire around and it will detect the fire properly most of the time. And I can move myself around as well to make it detect the fire a lot more consistently. If I go to the other side of the screen as well, you can see that it is detecting the fire properly, but on this edge of the screen is having a harder time to detecting it. If I put closer to the screen, it makes it a little easier to detect. But it's good enough, again, for a mockup. But the problem is, now I'm going to showcase you the problem that it needs more training, is that if I'm in front of the fire, it detects it with no problem, like so. And if I leave it here, where the background changes completely, like a mirror that is just, behind me, it doesn't detect the fire that well. But if I come back here, it detects the fire because the background change enables the model to detect fire a lot more consistently. And the same thing applies with this background because it's the same background that mirror is mirroring. So I'm here, the fire is being detected, as you can see here. I'm moving the fire around. It's okay. I go here. The fire is also being detected, but if I move myself away from here, it detects fire around my hand because of the lighting, and the background confuses the model, so it needs more training, as you can see here. But if I come back here, it makes the detection a lot more consistent again. So this is with the webcam. It's the video stream from my webcam. It works. But again, this is just a mock-up and it's enough for our testing. Let's move on to the showcase, where I'm gonna explain the idea behind the project, or the initial idea behind the project, and that's why we've done a mock-up, and we could improve on it and make it work for a real life case where you can solve real life problems with it. So moving on to the last showcase, now that we are able to detect fire in a single frame, and we are also able to detect fire in multiple frames, or in a stream of frames, essentially a video, the idea now was to have multiple videos being streamed, for example, a video server from CCTV cameras, and detect fire, or run this algorithm of fire detection in each of these separate videos. And then if fire has been detected, we would send an information, or a JSON data packet to another server that would be listening in a specific port or in a specific route, and then it would do something about it. For example, imagine you have multiple energy substations, and they have multiple CCTV cameras, each of them attached to a specific substation, and you detect fire in one of them. You send a JSON packet to the other server, and this server will receive this information. If fire has been detected, it would take an action of shutting down the transformer on that specific energy substation. That would be the idea of the of the project itself, right? So what we've done was we created a mock-up server where we will be streaming different videos from different CCTV cameras, essentially, and we would then have a separate threads. Each thread would be running this algorithm of fire detection on each of these cameras, and if fire has been actually detected, we would send to another server that simply listens to a specific route on /fire alert for post methods, and would then print us the information from which CCTV camera or from which camera fire has been found in, and you could improve from here and do another action, for example, shutting down the energy transformer. But this is just a mock-up idea, but you could improve from here. This is just a concept, and this project has been built around to try to solve this problem, or try to make a proof of concept. And for a mock-up, it works pretty well. So this is our simple Flask server that runs that streams these 4 different videos here. There are 4 CCTV cameras, and we can access them via this. This is our main code. These are alert.py. So this will actually access each of these videos being streamed on each of these specific URLs. So each video streamed by index here, and we will call the alert analyzer on each of these on separate threads, and then we'll be reading the frames from these videos and getting these frames and feeding our detect fire and smoke function that we've already went over on how it works. And if fire has been detected, we'll create a filter on top of the detection, because this function only detects fire on a specific frame, but we can't simply trust that one single frame equals fire. So the idea here is that we've implemented a simple filter on top of it, that we need to find at least 5 frames in a row that fire has been detected, and we're not in cooldown. So we've set up a cooldown of 120 frames, and so you can see here via cooldown frames. Oh, sorry, the cooldown here is 60 frames. So if we've sent a JSON package to the servers telling that fire has been found in the previous 5 frames in a specific camera, we enter a cooldown state, so we don't spam the server that fire is happening on a specific camera, and this cooldown is 60 frames. So as we are around 30 frames per second, this cooldown will be around 2 seconds. So this is just an estimate, okay? This is just a simple filter, simple algorithm that you can use to actually have a threshold of what is fire or what is not fire. And if fire has actually been detected, you send an alert. In this case, we decided to go on 5 frames just to test, and set a cooldown of 60 frames, around 2 seconds in this case. So let me showcase you how it works. So I'll start by running the server that hosts or streams these videos in those specific routes, and we can access the server here. And you can see that if you go to our browser and we access via index video, these different videos are being streamed currently in each of these routes, right? So in video number 2 here, or sorry, in the index number 1, video number 2, fire is already happening, but this is just the video being streamed, right? We're not actually detecting anything from it. We haven't started running our algorithm. And let's also start our second mockup server. It's a simple Flask server that listens on route fire alert for posts that if a data JSON packet has been sent, we're just going to print the data, the JSON data. So in this case, let's run the server. So it's now listening for for any information that is being sent to the server via post method. And here, the camera server recognized that we've accessed the URLs for each of these videos via HTTP. So now that we have both of our servers on, the camera server and the client server that's waiting for fire detection, we can call our code here that will look for fire in these specific cameras. So we have here our 4 cameras side by side, each of them being streamed on a specific video, and this one already has fire in it, and after 5 frames of fire being detected, it sends an alert, and we can see here that we've found fire in this specific camera here, camera 1, this timestamp, and the fire has been detected, and the time that was taken from the fire detection up to the sending of the JSON data packet. And here are the other 4 videos being streamed. The only problem is, of course, it's not efficient because the frame rate's not going to be that great. We have 4 threads running this separately on my single GPU, and we're doing it frame by frame for every single one of these 4 videos. But it's actually working for now. We could implement a better strategy in order for us to actually make it work without consuming that many resources. But as you can see, it works. And we, on top of sending the messages to this server, so this server would, for example, would have taken action here that fire has been found in the camera 1, so in the energy substation 1, and would turn off the, would shut down the transformer, for example. But in this case, we're just printing to the screen and actually logging here. We have a log file. Where is it? I'm trying to find it. So here, fire detection log. Here it is. So we're also logging things to this file, so we can actually take a look here and see if anything went wrong. We can take a look at the logging file as well. It's a simple logging file. But this is the idea of the project and how it looks right now, how it works right now. So here are the 4 streams again happening simultaneously. So I'll leave it at that for now. We could improve on it, trying to find a more efficient way to fire detect on multiple cameras to avoid hardware halting, and do it on a less intensive manner. But it's good enough for a mock-up. It's the idea of the project, and it's done its job. You could implement, you could develop from here, but this is just an idea of a project that you could take from this video and implement it yourself in a real-life scenario. So right now, I'm just going to explain a little bit of what the tools we have used a little bit more in depth and how they work. And if you want to do a similar project, I think it's very interesting for you to watch this section. If you just wanted to see the project in working here, this is how it is in the current state. As you can see, sometimes it doesn't detect properly the fire in some situations, obviously because, again, the model has been trained in a very small data set and it's not very consistent. But anyway, you could improve on the model that you're using. You could improve on the algorithm that you're using to detect fire and what you're going to do with it. So now let's move on to the explanation of the tools we have used and a little bit of how they work. And if you want to implement a project similar to this one, it might help you. So for our project, we initially wanted to start detecting fire on a single image and then move on to detecting fire on a stream of images and then doing something else with it, as you've seen on the showcases. So to solve the first problem of detecting fire on a single image, we've decided to use Ultralytics and the pre-trained model YOLO, in this case version 8. That was the latest version available at the time, and you can take a look here at their documentation. So YOLO stands for you only look once, so it's a machine learning model pre-trained for object detection, and that enables you, if you want to detect a specific object that it doesn't already detect, you can train on top of it and make it very efficient in a very short span of time. And in order for you to do that, you can simply use their library from Python using Ultralytics. You just import it and you tell which model you want to train on top of it. So this is our model, and we want to train on top of our data set. So you need a data set, and our data set we got from RoboFlow. If you come from RoboFlow, you can take a look at the site and search for your object you want to detect. In this case, I search for fire detection, and there are many different free options here that you can use for fire detection. And for example, here is a showcase of a dataset. You can just try to pre-train or download the dataset for using and training it yourself. And the hard part is actually creating the dataset, where you need a bunch of different images, and you need to usually manually go there and draw the bounding box where the object you want to recognize is at, and do it for the whole dataset. In this case, this dataset has 8,322 images, and as you can see here, someone has done this for us, and it's free. You can just simply download it, and you can but for YOLO, you have to put in this specific configuration here, where you have test, train, and validation. And you're gonna train your model on the train dataset, and you have images and labels. And how it works is that once you draw a bounding box, it will generate another text file, usually a text file, with the coordinates of where the bounding box is surrounding in that specific image, so that the model can understand where it should look for an object in different images. So you basically create a mapping between a specific image, so in this case this lighter on this guy here, and a text file of where the fire is in that specific image. And from that, the model will start to infer things from different images based on your training dataset. And it's very interesting if you can find many different situations where your object is in, and you can rotate and change the way that the object is in different scenarios, so you can more accurately detect object in different scenarios if that's your purpose, to detect your object in many different scenarios. So you should create a data set with those scenarios you want to detect that object in. That's why in that webcam showcase, the model was finding or detecting fire very consistently when I was behind it, because this is the only scenario where I have a lighter here in our data set, is a guy behind a lighter, and that's why when I was behind the lighter, the model had an easier time detecting the fire on the lighter. If we wanted to detect the lighter on different scenarios, we would have to enlarge this data set with more and more information of lighters being showcased in different backgrounds and such. So this is how the model will be trained on, and this is what we're using to train the model. So we're using Ultralytics library, using pre-trained model YOLO version 8, and we are using a free data set that already comes pre-configured for training for YOLO version 8. And after it trains the model, you can use a validation data set with different images or similar images. So the idea here of validation is that you can set a flag to stop the training beforehand if a specific condition or a threshold is reached. For example, if you're training your model and you're trying to detect if the error is decreasing or increasing, you could use your validation here to create this metric, and after each iteration, or after each epoch, or after each number of epochs your model has been trained on, you can run a validation on it and check if the error is decreasing or increasing. And if after some training the error starts to increase, it usually indicates that your model is being overtrained and is starting to become less and less effective, because this can happen in machine learning models. So you should stop the training before the number of epochs you've defined previously. And after that, you can run some tests on a test database to test if your model is detecting fire properly, and generate some statistics that, in this case, Ultralytics generate for us automatically on this runs tab, detect, and our training. And one of the most interesting things is this thing called confusion matrix, where you have the number the categories you want to detect. In this case, it's only fire, and the rest will be the background. And the idea here is that you can take a look on this matrix and see where the object you want was detected properly. So in this case, fire and fire, it means that it detected fire where it should have detected fire 954 times out of 1054 times in our test database. It means that it missed input 100 images where it should have detected fire, it detected background. Or in this case, detected fire where it should have detected background. And in 66 images, it detected background where it should have detected fire. So this is very interesting for you to see, and you can take a look at the diagonals to actually understand where it actually got it right. So in this case, our model has detected 954 out of the total images we had properly, and this is okay. And the most important thing is that inside weights, this is your trained model, and the best version of it is the best.pt here, the extension pt here, that you're going to use. So if you're satisfied with this model, you can use it, or you could simply retrain it. So instead of passing YOLOv8 now, we could pass the path to this specific model that we have already trained on, and we could train on top of this model, on top of this best.pt, to even further increase the capacity of fire detection on different scenarios. And you have to pass the data set you want to train on. In this case, we're passing this simple fire configuration, telling where are the training images, the validation images, the test images, and what we want to find in those images. In this case, we're trying to detect fire. This is the category we're trying to detect. And the number of epochs. So basically, the number of epochs tells the program how many times it has to go through the whole data set in the training phase. So 100 epochs equals we're going to train this model on this data set 100 times. So we'll go over the whole data set 100 times. And the image size here tells what is the image size you're training on. In this case, it's 640 by 640 pixels. And that's it. That's basically it. With like 3 lines of code, 4 lines of code, you can simply train your own model, and it's super easy. I'm also using my GPU in this case, so you can see here that I'm using my NVIDIA to train it. And one thing that I advise you, if you're gonna do it on your own graphics card, is that you find a way to dissipate the heat properly, because your graphics card will be catching fire. You know, it will be really hot, so you should find a way to dissipate the heat properly, because it will get a lot hotter than usually is. And you can see down here each epoch being trained. So it will divide your whole data set into batches, and it will train on those batches until it reaches an epoch, and you can see the progress of each epoch down here. After it trains the whole number of epochs you've defined, or if it has reached a threshold of error that you can also define here. So you can also define a way that it checks for error, and if the error starts to increase instead of decrease, it will stop automatically here on your validation set. But after you train on the number of epochs, it will tell us that it took, in our case, 1.2 hours, so approximately 1 hour and 12, 1 hour and 15 minutes to complete. And after that, you can use your model. So this is where your model will be, in this folder here, and you can use this batch.pt to build your project. So from here, that's where we started creating the fire detect to test it on images, and then on the stream of our screen, on our webcam, and then we've created our mockup servers to stream 4 videos. Each of them would be consumed by a specific thread that would run our algorithm, and then would spawn another thread to send the information to our second mockup server that will receive and print information that fire has been found on a specific camera. So that's it. If you need more information on how to do this stuff, you can take a look on the internet. There are different resources that show you how to download your datasets from Ultralytics. It's simple. You just click here. You can click here, view full project, and there will be a button for you to download the dataset, and you can simply learn how to configure and train your model using YOLOv8 here. They have their GitHub account as well, so you can take a look here at the GitHub. They'll have some specifications on how you can do stuff for object recognition and training your model on top of their pre-trained model. And yeah, that's it. Thanks for watching, and I'll see you on another video. Peace.